Okay, it's 5:25, so you know the drill. Two announcements. P-Set 4 solutions are up, so take a look at that. Any questions about P-Set 4 and or solutions? Okay. P-Set 5, finally the last P-Set, is due what day? Tuesday. So there's absolutely no chance I could extend that because it'll be way too late for the grader to be able to finish grading by the Friday, which is when grades are due. So we have to grade the final exams in 1.5 days.
We've been doing that already.
But the final's longer though.
That's true.
Yeah.
So
Maybe you should just make it shorter.
no chance. No chance. Any questions on P-Set 5? Please don't ask, what's a P-Set?
Yeah. What's on it?
Yeah, what's a P? Where do I find the P-Sets? Okay.
I don't know what I should say.
Yeah. Any questions about P-Set 5? Yeah. Go ahead, yeah.
Can we dedicate maybe off-hours today to doing some kind of final exam review?
So I'll talk about the schedule in a second.
Okay.
And I'll have an entire half day and office hours dedicated to that.
Okay.
But I mean, I can do final exam review today and office hours too, so.
Okay.
Other questions? So today we're going to continue with NP-completeness and maybe more. Depends on how much I want to do. Then Friday, God, can't type, I can't type or write. So Friday we'll talk about complexity theory. So this will be just a grab bag of lectures of things in complexity theory in a single lecture. So I think it'll be quite interesting. And then Monday will be my research for half the time. Then final review for half the time. And then office hours for final review as well. And then what's on Wednesday? Final. The day we play Super Smash Bros. No.
Yeah.
No.
If you could beat me.
Yeah, if you beat me, you get an A. Any questions on the schedule? I put this in an announcement as well, but it's worth repeating. Any questions on that?
So, Professor,
Yeah.
when you say that the finance will be calculated, is it going to be focused more on what we way, or?
So, if any of you know what the uniform distribution is, it'll be the uniform distribution over everything. So I'll try to make it so that everything is tested equally. So I'll try to make things not tested more heavily than other things. It's uniformly over everything. But of course, later stuff, like say ADFA, EDFA, that depended on our knowledge of DFAs, of course. So like things are dependent on other things, but like in terms of testing, it won't be any different. Other questions? Yeah.
What's the consensus on the cheat sheet?
I didn't get a single email.
Oh, okay, so 1 page.
So I think we'll do 1 page, but on bounded size, of course. Yeah. Yeah, as long as you're not disturbing the person next to you. Yep. I think someone brought a poster size sheet for midterm 1 and 2, so. Like literally poster size. So as long as it's not like multiple chairs long or anything. But The whole point of a single sheet is for you to think about critically what are the important things that we covered. What things do you think I will test you on? That sort of thing. It's not to like me trying to be mean or whatever. It's to make you think what are the important things, which I think is more valuable. I'm not biased or anything. Yeah.
Is there a correlation between cheat sheet size and test score?
It's actually inversely correlated.
Yeah, I thought so.
Because I've said this last time, but I've seen people just keep looking for their cheat sheet. I've actually seen an open book final, and what I've seen people do is just flip page after page looking for an answer, single pages at a time. They didn't study database theory. But yeah, that's the reason I want it to be so that you think critically what are the important things. Okay? Any questions otherwise? Yeah.
Might not be very related, but I have a friend who's taking this. Are you teaching this again?
I'm not listed for the fall, maybe spring if I ask really nice, but I have no idea. I'm hired by the department. They tell me what happens. I have no say, pretty much. Yeah.
You know who's teaching this next semester? Because I know Cole Board. Like, isn't he retired now? Or
No.
something?
No. Sabbatical. And I'm doing a different class. Intro engineering. Other questions, though? So I'll talk about the final structure maybe later, or I can do it today. So might as well do it right now, since we're already talking about it. So here's the final structure. Now I have a rough draft of the final, but now if I say anything about it, now I have to keep it in stone. Okay, so 300 points is a perfect score. And what are available, and I did this on purpose, there are 355 points available. I really did that on purpose. So the structure is 8 questions, which are the half sheets like usual, plus 1 extra credit. Yes. No. No. Nope. And so the 8 questions are alternate between 35 and 40 points each.
Can we expect similar difficulty?
Yeah. Yep. Mm-hmm. Yeah.
True false or no true false?
So there are no true false. But the first question is language classification. So what it'll say is that I give you a bunch of languages, and what I want you to say is the most restrictive class for which this language is in. So if the language is context-free but not regular, you'll say context-free, for instance. Yeah.
Any recommendations on how to practice for that?
Review the languages that we've seen and the properties, like closure under intersection for certain things. Yeah, that'll be definitely helpful. Yep. And the other ones are problems, similar type problems that you've seen before, plus material from the last 2 P sets, which hasn't been tested, so, but it'll be the similar type flavor. Other questions? No questions? No. Well, because it's not really fixed in stone, so I can't really talk about something that's not fixed. Yeah.
When you say 8 questions, is it actually 8 questions, or is it
Well, there are sub problems on each. I think it's between 2 and 3 sub problems each. Yep. Just like the midterms. Yep. Yeah. Oh yeah. Very very important. 125 minutes. So the entire last class from start to finish. So 5:25 to 7:30.
Will there be office hours after?
No, that's why I'm holding office hours on Friday. Yeah.
Is the difficulty going to be similar to the first one?
Yep. Exactly the same, just longer, obviously. Yeah.
So it's doable within 75 still, and then you have like.
It's scaled up. So 5 and 75 minutes. If you scale it up to 8, that's 120 minutes. So I gave you 5 extra minutes. Yep. Other questions? If you've been doing the daily exercises, it won't be that challenging. You won't see anything. You won't be surprised. How about that?
Is it possible that, I think we've asked this before, but for the daily exercises, I know you answer like certain things, but there's no like real answer for that. Can we get some sort of like concrete answer for at least even the last few? Because this topic has been like a little bit more.
If you send me an email, then if there's enough consensus of whether there should be solutions for them, then I can certainly do them, but send me an email.
So what is the material that we can just directly reference, like the proofs from the book concepts, for example, the theorems, can we just reference them in the...
Oh yeah, sure. If you like want to use the fact that 0 to the n, 1 to the n is not regular, say we prove that in class. Yeah. Don't make it... unless the question literally says prove that 0 to the n, 1 to the n is not regular, then you can't say, oh, we proved that in class. Because that would be, yeah, totally easy at that point. But I guarantee that won't happen. That situation won't happen.
But
Yeah.
As far as that goes, what is the material that we can release? So
Yeah. Anything that we've seen in class or the book or recitations. Yep. Or P sets or Piazza. All of those resources are available. Not like literally available as in you can look them up, but you can reference them in terms of writing it. Other questions? Yeah. Yes. Mm-hmm. I don't know what Andrew's going to do. You can email him if you... It might be final review. I don't know what he's doing.
He said yesterday for sure.
Okay, so it'll be final review. Other questions? Okay, so let's get back into NP-completeness stuff. So we showed last time these 2 classes of languages, P and NP. And P represents things we can solve deterministically in polynomial time. And NP is the set of all problems we can solve non-deterministically in polynomial time. So efficiently, deterministically, and non-deterministically. And one of the major questions of computer science is, are these things different? Well, we know that P is a subset of NP because we don't have to use non-determinism to solve a problem. So if we remove non-determinism, then we have just the class P right there. So what the major question is, are there any problems we can prove are in NP but not in P? Which means a normal deterministic computer can't solve those problems efficiently. And we don't know if that's true or not. It seems to be true. But the way we were able to get some intuition of that is this idea of NP-completeness. So we showed what a language means to be NP hard, which means if this problem happened to be easily solvable deterministically, then every problem in NP is solvable deterministically within a polynomial amount of time. And then NP completeness is just NP hard plus you're also an NP. Okay? And the problems we were able to show were NP-complete were C and F set, which is formulas that are of the form, let's see how I can say this, ands of clauses, and clauses are ors, not two S's, ors of literals. And we showed that this was NP-complete because since we didn't have an NP-complete problem before to work with, we knew that since every problem must reduce to this problem, we know that every single problem in NP must have some non-deterministic Turing machine that runs in polynomial time. And so what we did is we looked at the accepting computation history of that machine and transformed it into one of these formulas. And so if this formula is satisfiable, then the original Turing machine had an accepting computation on that input. Yeah.
And satisfiable again means?
There is some way of setting true and false to the variables of the formula to make the formula true. Yeah. It could be that there are a lot of satisfying assignments, but we need at least one. Yep. And that's how we were able to show that CNF set is NP hard. Well, it's in NP because the only thing we need is a certificate to say that the formula is true. And a certificate in this case would be the actual assignments to the variables of the formula. And then we could just check, is the formula true within a short amount of time. Okay? What was another problem we showed was NP complete? The Clique problem, or Clique problem. And yes, Super Mario. Yeah. It's graphs and an integer, and I should say as input, and determine if there is a complete subgraph on k vertices. I should say that CNF set determine if formula is satisfiable. Okay, so we showed that CNF set was NP complete, but we also showed that Clique was NP complete. And the way we showed that is, well, we had to show that it was in NP and is NP hard. Well, it's in NP because, I lost my words. A certificate for this problem would be, just give me the k vertices that supposedly may or may not be an actual complete subgraph. Well, then once I get those k vertices, I just determine, is that actually a complete subgraph in the original graph? And I can do that deterministically in polynomial time. So that's fine. But it's NP hard because we were able to reduce it from CNF set. And the way we did that is this gadget type proof, where we had a bunch of vertices for every clause, and we connected edges, every single pair of vertices, except those among the same gadget, and ones where they are complements of each other. So if we had x1 in some vertex gadget and x1 bar in some other gadget, we do not connect those up. And we talked about how that is a true reduction from CNF set last time. But we can do that in polynomial time, and therefore Clique is NP hard. Okay? Any questions about those two? Okay, so let's talk about one more. Actually, no, several more. So I want to talk about this problem called vertex cover. And I'll abbreviate it as VC. So what we're given is just a normal graph and integer k, just like before. And our task is to determine if there is a subset of the vertices of size k so that the vertices in the subset are incident to every edge. So the idea is we supposedly can pick k vertices of this graph, and we want to determine if there is such a picking of these k vertices such that they touch every edge of the graph. So let's do an example I'm going to make up on the spot. Let's see. So let's make a simple graph. Okay, that's pretty simple. Okay, yeah, that's a pretty good example. So here's a graph. Is there a vertex cover of size 1 in this graph? In other words, can I pick one vertex and have that one vertex be incident to every edge of the graph? No, because even if I pick this vertex in the middle, well, I'm not going to touch the two edges on the outside. That actually tells you something. Could I have a vertex cover of size 2? No, because even if I pick that one and I pick one of the vertices in the other two edges, I'm still going to have one edge left out. Is there a vertex cover of size 3? Yes. So, for example, I can pick that vertex, this vertex, and that vertex. And those three vertices are incident to every edge in this graph. Okay? Suppose that you're given this graph in an arbitrary integer k. What is a brute force algorithm that you might try? Well, just look at all k choices of vertices and see if they touch every edge of the graph. Well, if there are n vertices, then that's roughly n to the k different choices, right? Wait, doesn't that mean we can solve it in polynomial time? I can solve it in n to the k time. Is that polynomial? I don't think so. Why is that not polynomial? What if k was like n minus 1? Then that would take n to the n minus 1 time, and that's definitely not polynomial. And this k is not a fixed integer. In order to say that vertex cover runs in polynomial time, I need a fixed integer that works for all graphs. But if I take my input integer and make the runtime based off that, that's not a fixed integer. So even if it was a small number like 2 or 3, that is not a fixed integer, and therefore it's not polynomial time. That does not mean that we can't solve vertex cover in polynomial time by some other method. Okay? But I want to prove that this is NP complete. And so therefore we can assume that there's probably not a polynomial time algorithm for this. So I want to say that VC is NP-complete. If I want to show that this is NP-complete, what do I need to do? Show us an NP. Okay, let's do that guy. How do I show that VC is an NP? What thing do I need to show? Yeah, I could show a non-deterministic Turing machine, but what's an easier way? It starts with cert and ends with ificate. Right. I need to show a certificate that I can verify deterministically whether or not the thing really does have a vertex cover. So what would a certificate in this case be? To verify that there really is a vertex cover of size k. Yeah, the set of k vertices, right? If I'm given the set of k vertices, say non-deterministically, could I verify that that set of k vertices really is a vertex cover? Yeah, so what I do is I look at every single edge and see, does every single one intersect one of the vertices in the k set? And if they do, then therefore we're all good. And how many edges are there? Well, only polynomially many. So therefore, we can verify this in polynomial time. So certificate is the set of k vertices. And the reasoning is almost identical to the Clique problem. So pretty much after this point, I'm not going to say how to verify this because it seems pretty obvious how you would do it. Just look at every single edge. But so I'll just say the certificate is this, and then it seems pretty clear what you need to do after that. Okay, we showed it's an NP. Now what do I do? Show it's NP hard. So of course this is always the hard step. No pun intended. So if I want to show that it's NP hard, what do I do? Yeah, I can use some other NP-complete problem that we know to work with. What NP-complete problems do we know so far? We know Clique is one, and CNF sat is also one. Okay? Well, so now it becomes an issue of figuring out which one to reduce from to make our lives as easy as possible. In fact, you can actually use both, and also any other NP-complete problem, but we just need to choose which one of these two we're going to work with. So we're going to take a slight detour first, sadly. We'll come back to it. So we talked about CNF sat before, but the clauses, we never restricted how many variables could appear in a single clause. But I want to show that if you restrict it to exactly 3 variables per clause, it remains NP-complete. And that problem is called 3-sat, or 3CNF-sat. So 3-sat, also called 3CNF-sat. It'll become evident why I want 3-sat here. So this is the same as CNF-sat, but every clause has exactly 3 variables. There are other variants where you say at most 3, but we can actually avoid the less than here. We can just say exactly here. And we'll show even if you have fewer than 3, you can up it to 3, and there's no problem there. Okay. Well, is 3 sat in NP? What would a certificate be to verify whether this formula is satisfiable or not? Well, how did we verify it for CNF sat? Well, what we did is we gave you the variable assignments. So we say, set that variable true, set that variable false, and for the rest of the variables as well. And we just looked and said, is the formula actually satisfied by that assignment? So here is exactly the same. The certificate is the assignment, I should say truth assignment of variables. And if I want to show that 3 sat is NP complete, I need to also show that it's NP hard. So now we're almost at the same situation we were with VC just a minute ago. What problem do we want to reduce from? Well, we can do CNF sat or we can do Clique. So the art of doing these is to figure out what is the closest problem to make our lives as easy as possible. Well, I think CNF sat is really close to this one. So let's try that one. So we're going to actually show that CNF sat is polyreducible to 3 sat. So if I wanted to show this, that means I gotta transform my, I should transform an arbitrary CNF formula from CNF sat and transform it into a 3 sat formula such that the original was satisfiable if and only if the one I get is also satisfiable. Okay? So I'll just write it like that. So we're given CNF formula, and we're going to output a 3 sat formula. And we want the original CNF formula to be satisfiable if and only if this guy is also satisfiable. So I don't want to have the original formula be satisfiable and the one I make be not satisfiable. We want to preserve the answer. Well, let's see. I'm going to be given some formula that looks like X or Y, maybe not Y, and Z or A or B, not let's say, or C, and X or A or not C, and etc. Maybe we'll do one more and just a single X, bar let's say, and etc. So in the original CNF formula, we never restricted how few or how many variables could appear in a single clause. Well, if they have exactly 3 variables already, do I need to change that clause? No. So we're going to look at each clause. If exactly three variables do not modify. I suppose we could modify it, but I don't want to change the answer as to whether it's satisfiable or not. Okay? Well, If it doesn't have exactly 3, it either has 1, 2, or at least 4, right? So what if it has exactly 1? So it's of the form x, let's say. How can I modify that clause so that it has exactly 3 variables and with the exact same truth value? Yeah.
Could you say the same thing 2 more times? Like
Yeah.
X and X and X.
X or, yeah. Yeah, so if I do x or x or x, that doesn't change the truth value, right? So we're going to modify that to be x or x or x.
And you want to keep variables, you want to do X or 0.
Well, we don't have an XOR operation.
Or not, I mean X or 0.
Well, I should have chosen a different variable name.
Okay.
Yeah, the variable x or, yeah.
So why can't you do and in this case?
Because we're looking at individual clauses, because they don't have the right number of variables in general. So the problem says you have exactly 3 literals. Sorry, 3 variables per clause.
Is it more of a correctness thing? Is it true and true and true?
Well, remember CNF, conjunctive normal form, is ands of clauses, and clauses are ors of variables. So I don't want to modify how the clauses work together. I want to modify individual clauses. Yeah. Okay. Well, I'm sure you know if we have exactly 2. So let's say we have x or y. These may or may not be negated. I'm not depicting that. But how can I transform x or y to be exactly 3 variables per clause?
Add one more either?
Yeah, add 1 more of either. Yep. So maybe we'll do x again. And that definitely doesn't change the truth value of that clause. So remember, we don't want to change the truth value of it. Just like for Chomsky normal form, the other CNF, we didn't want to change the language of the CFG. Here we don't want to change the truth value of the clause. Okay, well, now it becomes an issue for at least 4. I can't just keep adding variables to the clause. That'll make the clause longer, and I want it to be exactly 3. So what we're going to do is, if it has at least 4, we're going to be able to reduce it down by 1. And then add another clause. And then we can do induction to show that we can just keep doing this iteratively until we get down to 3. So without loss of generality, let's suppose it has exactly 4. And then therefore we can apply this to larger and larger clauses in the same way. So if exactly 4, so I'm going to put it down here. So where's my notes? So let's say it's x or y or z or w, let's say. Well, now we got to think a little bit about it, because I don't want to change the truth value of this clause. And I clearly have to split it into multiple clauses, for sure. But it's just, how do we do the split? That's the important thing. Well, maybe what we can do is we can split it up into 2 clauses, and we don't want to change. Wait, you had a question?
Yeah, I was wondering if this is where the non-determinism is going to come
No. We have to do the reduction deterministically. The problem can be solved in non-deterministic polytime, but we're doing the transformation deterministically. Yeah. So this has to be deterministic. And that's interesting. Non-deterministic reductions. I haven't really thought of that. All right. So we don't want to change whether or not X, Y, Z, and W are negated or not. So let's say that we want to split this up into two clauses, and we don't want to change whether or not X, Y, Z, W are negated. So let's keep them unmodified. And one way we can do this is, well, if I have this be X or Y or Z over here, that's going to cause a problem. Because what if W was the only true variable in that clause? Then we're toast. So we can't do that. And similarly, I can't put 3 of the original guys in the second one. Yeah. So let's put 2 of them in each of them. Well, we got to put something as the third element of both of them. Well, it can't be one of the original 4 because we want to keep. Yeah, we can't keep one of the original 4 because for the same reasoning. One of the other variables might have been the only true thing in that clause. So maybe what we can do is force a variable to be false. Force maybe a brand new variable to be false, and then therefore I must pick the other ones exactly as I did before. So there are many ways you can do this, but one way is to introduce a brand new variable, let's call it A, and make it negated in the other one. Well, let's see. If the original, if there was a way to satisfy the original formula, therefore we must satisfy the original clause, which must mean X or Y or Z or W, that one of those is true. Well, is it still true here? Well, if it's the X or Y one, like X or Y was one of the ones to be true, well, that clause is satisfied. Then I can just pick A to be false. So therefore I'm satisfied here. If it's on the other side, one of Z or W is one of the true ones, then I can set A to be true. Well, that's good, but what if the original clause wasn't satisfied? Which means X, Y, Z, and W were all false, right? What if that was true? Could I satisfy these 2 clauses? Well, if I pick A to be true, I don't satisfy the second one. And if I pick it to be false, I don't satisfy the first one. So there's no way I can still satisfy both clauses. Okay? So this type of alternation right here, when you introduce a brand new variable, is used a lot when you're working with satisfiability proofs like this. If you want to have a change in structure, then it becomes quite easy when you're doing reductions of this form. So the idea is we have this large clause, and we don't want to change its truth value, so we split it up into 2 clauses, add a new variable so that we force the original assignments to have the same truth value afterward as we did before. So if it was satisfiable before, it's satisfiable now, and if it wasn't satisfiable before, it's not now. Okay? What if we had 5 variables per clause? Well, if we apply this process, I'll have 4 in the first one and 3 in the second. So then I just apply it to the 4 one. And then I'll get a 3, 3, 3 with a brand new variable every time. Okay? Is that all I need to show? Well, the formula I get at the end does have the same truth value by induction as the original formula, but what else do I need to show? What I better not hope about the reduction. What? Yeah, if it ran longer than polynomial time, I'm in trouble, right? So does this run in polynomial time in the size of the formula? Well, let's see. If we had 3 variables, we don't touch the clause at all. If we have 1 variable, then we just add a constant number to that clause, so constant. If we have 2, we add a constant 1, so that's fine. If we had k variables in a clause, that's at least 4, then how many clauses do I add? Well, every time I remove one from the k length one, then I'm going to have an additional clause. So at most, I'm going to have k minus 1 additional clauses per clause. So let's just say every single clause was too long. Well, if everyone had k variables, then I'm going to only add k minus 1 additional clauses, which is a polynomial. And if there are polynomially many clauses, I still have a polynomial number of clauses at the end. Okay? Because it's only k minus 1 times however many clauses there are, which is certainly polynomial in the size of the formula. Okay? So this reduction takes poly time. Okay? Any questions on that reduction? Because we're going to use 3 set right here. Okay, so let's bring down, I'm going to copy this down. So let's go back to vertex cover, unless there are other questions. Okay, so vertex cover, remember, is we're given this graph and k vertices, and we want to determine if there's some selection of k vertices that touches every edge. Okay? And I claim that this problem is NP hard. Well, now we have CNF sat, 3 sat to work with, as well as Clique to work with. Well, we're going to actually use 3 sat right here. And the reason we'll use 3 sat is that the structure of 3 sat is really useful in a lot of proofs. The idea is if you have exactly 3 occurrences of variables per clause, then it becomes a lot easier on the structure. And we'll see that in the proof right here. Whereas if I had arbitrarily many per clause, then that will throw off the structure entirely. And the notion of using sat, where each variable only has 2 possibilities, that's also really helpful. So like in the Super Mario proof, we had 2 different possibilities as to what Mario could do per variable. Okay? Cool. So let's say that the variables in formula are x1 through xn. No, so we're reducing 3 sat to vertex cover, which means that we're given an arbitrary 3 sat formula to turn into a graph. Yeah, so I should say, we're given a formula, a 3 sat formula, and we want to turn this into a graph and an integer k. So we want the original formula to be satisfiable if and only if the graph that we produce at the end with the integer has a k vertex cover. Okay? So we're going to use as I mentioned last time, a gadget proof, like we did last time. So the idea is we make a gadget for each variable, then we make a gadget for each clause, and then connect the two. Okay? So just like in the Super Mario one, we had a variable gadget which had the two possibilities, a clause gadget which is the three possibilities, or K in general, for Mario to hit the star area where the star will bounce around and he can get it to pass the fire bars. Here we're going to do a similar type thing. So remember, the variables have two possibilities. Either they are in the positive form or they are in the negated form. So a variable gadget will be just two vertices with a single edge for each variable. So if this one happens to represent x1, this gadget represents x1, then we're going to have two vertices, one representing the positive form of that variable and the other one representing the negation of it. And if we had other variables, we'll have x2 bar, and then xn bar. And we know that each of these variables appears in clauses. So let's say the clauses are C1, C2, up to, let's say, Cm. Okay. Well, what are the clause gadgets? Because I know that this is a 3-sat formula, I know that there are exactly 3 variables per clause. So what we're going to make is a triangle, a complete graph on 3 vertices for each of the clauses. So make a triangle right here. So that's clause 1. This is clause 2, and let's say that there are m of them. Oops. Well, ignore the clause gadgets for a second and just look at the variable gadgets. What is the minimum size vertex cover for just the variable gadgets, if we included all of them? Well, could I get every single edge with one vertex?
Oh, you mean like not within each gadget, but for all of the gadgets?
If I include all of them,
It would be X or N, right?
it'd be n. Well, that means I'm picking one of the possible 2 choices, which means I'm setting that variable to be, or if I'm setting x1, for example, I'm setting x1 to be true. If I happen to be setting x1 bar, that means setting x1 to be false. And so now what we got to do is we got to connect the variable gadgets with the clause gadgets in order to keep that possibility. So let's say that C1 is, oh, I don't know, x1 or not x2 or xn. Well, it doesn't actually matter, but let's label the vertices of the clause gadget. So let's say the top one was x1, this one is, actually I'll make the top one x2 bar, because I don't want the picture to be too bad. Xn there. And so how am I going to hook them up? I'm just going to hook them up to the respective very literal occurrence. So for example, x2 bar, that'll be connected to x2 bar. x1 will be connected to x1, and xn will be connected to xn. And I repeat this same process for every clause. Okay? Well, let's see. Remember, how many vertices of the only variable gadgets do I need to have a vertex cover among them? N. I need n of those. So how many do I need in general for this entire thing? Well, I need k to be n plus something. How many should I pick of each of the clause gadgets? I need 2. Can I get away with 1? No, because no matter what one of the clause gadgets I have, I'm going to still have some edge that's not there. So I claim that k in this case will be n plus 2m. So I should say this is Cn.
And M is
Yeah, m is the number of clauses. And of course, n is the number of variables. Yeah.
The connections between the clauses and the variable gadgets, are those connections edges?
Yeah.
Or are those
Mhm.
indicating that the x1 in the variable gadget is the x1 in the clause gadget?
So if it's xi up in the variable gadget, I connect it to every occurrence in every clause gadget where there's an xi.
Okay, but is that an actual edge?
Yeah, actual edge.
Okay.
Yep. Yeah, everything here are vertices and edges.
So there you have, in C1, you have the x1 with an edge to x1.
Yeah. Yeah, so I'm connecting them to the respective variable gadget and the positive or negated one as the case may be. Okay? All right, so why does this work? Well, let's see. If the original formula is satisfiable, do I have an n plus 2m vertex cover? Well, let's see. Look at the assignments of the variables. Choose those as the assignment, the parts in the variable gadgets to be, pick those ones in the variable gadgets in the vertex cover. So let's say, for instance, that in the assignment we make x1 true and x2 false. Then I'm going to pick those in my vertex cover. Well, let's see. At the end, I need to pick 2m other vertices. Well, I'm just going to pick, I'm going to pick the ones in the variable gadgets, at least one of them that are, I'm going to pick the ones that are satisfied by the original assignment. No, I'm not going to do that. So what am I going to do? What I'm going to do is, well, if I happen to, sorry, I thought of what the construction should be. So if I happen to pick, let's say, x1, well, should I pick the x1 down here? I mean, I could, but is there any reason I should? Well, it's covered by the x1 up here. So I pick the other two. Okay? Well, the formula supposedly is telling me which of the variables in each of the clauses is the one to make the clause true. Well, we pick that one in the original, Yeah, we pick each one of those in the variable gadget and the other two in the clause gadget. And then therefore we have an n plus 2m size vertex cover.
Because the x1 in the variable gadget covers the adjacent vertex between the x1 and clause, and as well as the length between x1 and the x2 bar and x1 covers.
Yeah, so it's just the notion of if we have a satisfying assignment, how do we map that to a vertex cover in the graph? Well, if you think of satisfying assignment, that's just setting x1 to be true, for example. Then we're going to pick the one of the two possibilities in the variable gadget. That's the one we're going to pick in the vertex cover. Then we don't need to pick the one corresponding to it in the clause gadget. So we just pick the other two. Okay? So that's one direction. What about the other direction? If we have an n plus 2m size vertex cover in the graph, do I have a satisfying assignment here? Well, let's think of it an even easier way. If I don't have a satisfying assignment in the formula, do I not have a vertex cover in the graph? Well, if I don't have a satisfying assignment, then I can't pick the variables appropriately in the variable gadgets, which means I must eventually be able to pick, no, I must be forced to pick in some clause 3 vertices. But if I pick 3 vertices, let's say these 3, then there's no way I can still have n plus 2m and get every single other edge. Because either one of the two variable gadgets is one of the variable gadgets is lacking, or one of the clause gadgets is lacking by some edge. So therefore, I don't have a vertex cover now. But
Can you give an example of that? A concrete example of that?
sure. So let's give an example. So let's say we have let's do 2 clauses and 3 variables. So, or not x2 or x3 and x1 bar, or let's make the negation of it. So just like the construction, we have 3 variable gadgets. And since we have 2 clauses, we got to make 2 clause gadgets. So let's make this x1, x2 bar, x3. This is x1 bar, x2, x3 bar. And then like the construction, I'll put it in a different color. Let's make it orange. So x1 gets mapped to x1, x2 gets mapped to not x2, and x3 gets mapped over here. Oh, and these have all connections. And then for the other one, we have x1 bar connected to there, x2 connected here, x3 there. Okay. Is there a satisfying assignment for this formula? Is there a way to satisfy that formula? Yeah, certainly. So let's set x1 to be true. What else do I need? x2 to be true and for fun, let's set x3 to be false. So this formula is definitely satisfiable. Well, what would a vertex cover in this graph look like? Well, the way that we can see it is just pick in the variable gadgets the appropriate things. So if we pick x1 to be true, we pick that guy in the vertex cover. We say x2 is true, we pick x2 in the vertex cover, and x3 is false, we pick that guy in the vertex cover. Well, just like in the construction, we need to pick 2 vertices at least in every one of the clauses. So which one should I pick? Well, for the first one, we can pick x2 bar and x3 because there's no point in picking x1 for the clause gadget, I mean. And for x3 bar, we can pick x1 bar and x2 because there's no point in picking x3 bar. Okay? Well, this actually kind of helps us with the correctness argument. Well, if I have a satisfying assignment, I just showed you how to get a vertex cover in the actual graph that we make. But what if we had, so we have 3 variables and 2 clauses. So that's 3 plus 2 times 2, so that's 7. So could I have 7 choices of vertices here and not have a satisfying assignment in the original formula? Well, let's see. If I pick 7 things, then if it's not of this form where I have exactly 1 per variable clause and 2 per clause gadget, well, suppose that one of the original if one of the original variable gadgets didn't have 1 up there, well, if I didn't pick either one of those 2 vertices, I'm missing that edge now. So therefore, that's not a valid vertex cover. And if we only have 1 vertex picked per some clause, then I'm missing an edge right there. And so now all we need to do is just read off which of the assignments we just made in the variable gadget. So like in this case, since it is of the form exactly 1 variable picked per clause, per variable gadget, and 2 vertexes per clause gadget, then we just look at the assignment. So here we saw that we have x1 set to true, x2 to be true, and x3 to be false. Okay? So all we're really doing is we're forcing picking exactly 1 of the 2 possibilities per variable. And the way we do that is for that variable in the clause part, we've already picked that guy. So we have to pick the other 2 in order to get a valid vertex cover here. Yeah. Yeah, so I'm just doing that as a correctness argument. Yeah, so I marked that here. Yeah. That's not, yeah. Yeah, it's kind of hard. Is it hard to see? I did it in red. Yeah, so based on my assignment, x1 true, x2 true, and x3 false, those are the ones I picked in the vertex cover. And then I picked the other 2 in each of the clause gadgets. Okay? And for example, if we had, instead of x2 false in the original formula, we had x2 let's make x2 false in both of them. So that we have I'm trying to think of an example where we have 2 connected variables up. So if we, for example, have x3 to be, if we pick x3 to be positive in both variables, then we'll have connections that look like, let's see, like that, I think. Yeah. So here we have, and a satisfying assignment, of course, is making everything true. And if we make all three true, then that means I have picked x3. But that means I have two, for the first clause, I have two things that I can ignore, right? So for x1 and x3, I can ignore both of those, right? But, so now all we need to do is just pick two arbitrarily and make sure that we actually don't have to pick x2 bar in this case, but we have to pick two no matter what for the first clause gadget in this case. Okay. For the I forgot to update that, so that should be x3 like that. Yeah, I was just updating it so that I have two of the original assignments coming into the same clause. So therefore, we would have to pick two. We still have to pick two of them, but we can pick two arbitrarily instead of being forced. Okay? I think we're over time for the first part. Any questions about the reduction? Okay, so let's take a 5-minute break.